In this video, I'm going to go through an overview of what we're going to cover in the HSC course, the engineering course, for the first topic, which is civil structures. Okay, so we're going to be spending a term. We actually will probably spend more time on civil structures than we do on the last two. So the first two chapters take up a lot more time than the third and fourth chapter. So we're going to go through that. So always that we follow the same pattern, which is we have historical and social influences, and then we will go through mechanics. We'll go through materials and communication. So communication is going to be graphics, and we have to do a report. So the report has to be done in civil or personal. Public, we're going to do our report in civil. So that is a pretty standard. The key things we're going to point out here. Okay, so when we do mechanics, the big thing that we're going to learn this time around is trusses and bending. Now, I think bending is incredibly important. Unfortunately, it tends to be under-tested, in my opinion, in the HSC. We learn about stress and strain, but I don't think there's anything we learnt that you have not already learnt in Year 11. Okay, for testing materials, again, I try to teach the testing material stuff as much as I can early. Now, crack theory, if you look, see, there's quite a bit of stuff here on cracks. Now, look, cracks really trigger me. I have a lot of cracks in my apartment, and also there's like 5 pages in the textbook on cracks. Whereas I think you could sum up cracks in one line, which is, if you have a crack and you want to stop the crack from growing, drill a hole at the end. That is it, right? Literally, I've told you everything that you need to know about cracks, but we will go through the book. Ceramics, so that's obviously going to be cement and concrete. It's also going to be bricks, glass. We've already learned about glass. Pretty much all I have to teach you about glass we've already done. We're going to learn about composites. Again, we've covered pretty much everything here. We haven't talked about geotextiles very much yet. Concrete is considered composites, but we also learn about ceramics. Corrosion is a big topic. So corrosion is something we will probably spend several lessons on. Okay, then we're going to talk about recyclability materials. Again, not a huge amount that I have to say about this. There is more and more we are working on trying to reduce them. We always try to reduce the amount of materials we use. There is an option for like reverse garbage where people can, if you dispose of things well, that we can reuse these materials. Crushed concrete can be used as road base and things like that. But ultimately, it's not something we focus heaps on. So just putting that a heads up. When we get to Australian standards, the big thing that you're going to be assessed on in terms of your assignment is going to be dimensions. Now, I didn't focus on that much last year. This year, I'm going to focus more on dimensions. Okay, we're also going to do a little bit of sketching. Again, we haven't done much sketching in last year because there's just not a whole lot of marks in the HSC. I'm going to probably give you more homework to do this year on sketching. And we'll have to do CAD as part of this assignment. So that's going to be a couple of changes. Okay, so that's what we're covering. That's what we have to do in the next 10 weeks or so. And what are we going to have a look at as well? Okay. In terms of the description of what does civil engineers do? Well, we've got different kinds of civil engineers: structural, transport, hydrology, geotech. So civil engineers are responsible for the design and management of structures and infrastructure projects. This includes things like water supply, so pipes, transport networks. So it also includes structural engineering, which includes things like buildings. It can include things like towers, airports, a whole bunch of different fields. Okay, when we look at civil engineers, their roles and responsibilities, civil engineers need to design solutions for infrastructure needs. Right, so everyone has to design solutions. All engineers find solutions. They find infrastructure needs solutions, right? Everyone has to worry about social and cultural impacts, health and safety. All engineers have to do some calculations. They calculate forces. They apply knowledge of materials to design structures adequate to withstand those forces. So the big thing, I'm going to sort of step back for a second and say, so what do civil engineers do? Well, they have to figure out or guess what is a reasonable amount of load that a structure needs to take. And once they've figured out what it needs, they design something that's going to be suitable. Now, it is impossible to make something that will never break, right? Because if the mother of all earthquakes hits your bridge, right, you're not going to be able to design for that. And it wouldn't be cost effective, right? Something I say many times is anyone can build a bridge. It takes an engineer to build the cheapest bridge that is just good enough to reliably not fall down, right? So to withstand the forces that we have calculated, or the forces that are specified by our these standards. In our case, the Australian standards. Okay, we consider economic impacts. Now, look, this is one of the things we often undersell, but in actual practice, if you can't make money, right, you can't pay the bills, you're no longer an engineer, right? If you can't pay for your wages, you have to do another line of work. Very few engineers can afford to do it for free. Okay, now you have to plan and supervise construction, or you have to supervise the design, but there are civil engineers who supervise construction. Right, probably the majority of engineers who work as civil engineers, they're probably more focused. There are more who are focused on the construction side than there are who are focused on the design side. And I think that a lot of people are surprised at that. A lot of people, especially very book smart nerds, say, "Hey, I want to go be an engineer because I like maths," and then they find out that 2/3 of engineers work in construction, and it's a very different world. So when you're a designer, you wear a tie and you go into work in a nice air-conditioned office, and whereas when you're a site engineer, you're wearing the denim work high vis and a hard hat, and it's how many times you have to swear at someone to get a job done. Also, civil engineers are in charge of maintenance and operation. So a lot of civil engineers work for councils, and their job is just going and maintaining the roads, filling in the potholes, doing the little bits and pieces here and there to make things better. Okay, so that's what civil engineers do. We can close that. I wasn't going to focus too much on these syllabus outcomes. Okay, what I'm going to look at now is what the book has to say about what civil engineers do. So for this chapter, the book is divided in the same way. So we've got historical and civil developments in civil structures. It talks about how they're focusing on bridges rather than dams or pipelines or something like that. We've already covered that in other videos, but I will pause this to show another just quick summary of bridges that will kind of give you the main points that we want to look at. Now, I did show this briefly when we were talking about bridges in the history lesson, but this would be a very quick and effective summary. So this is an Airbus A380. Most of you guys have seen one of those. This is the Titanic. It was a big ship. So this is giving you a perspective of 100 meters. So we have old bridges like Trajan's Bridge. We have the Rialto, which was the revision of bridges when we had the Renaissance. This is London's Tower Bridge. And then we have the Forth Bridge, right, which is quite, like, you can see roughly how that's a very, very long bridge. Here we have the Sydney Harbour Bridge. We have the more recent, I'm not going to, Chow Tien Men, but I'm not going to try and do the tones. Then we have the Golden Gate Bridge, which was the longest bridge for a very long time. And now we have the Akashi Kaiko Bridge, Akashi Kaiko. I don't care enough to try and pronounce it properly. Bridge, which is huge by comparison. And then we have the Millau Viaduct, which is in France, showing that is, just remembering that is as tall as the Eiffel Tower, that tower there. Okay, so that's a rough summary of bridges. And that's enough bridges that you could talk about the significance of those. You could pick two of those and compare them and say, how has these innovations come about? Well, improvements in design, improvements in materials. Yeah, so an improvement of design means that we can design more effectively and more efficiently. Improvements in materials allow us to build more bridges more economically. Okay, so I can close that. Now, what I'm going to go on to, so environmental implications of materials. Okay, so we'll go through that. Okay, so the next big thing, the big focus on this topic is trusses. So trusses, we're going to talk about reactions. We're going to talk about different kinds of reactions, calculating reactions using moments. We're then going to learn how to calculate trusses, and because that goes on for quite a while. Like I said, it's an important part. We're then going to learn about bending and do bending calculations, which in my opinion are the most important thing as a civil engineer to know, even if it's not tested very much. Okay. Moving on from there, I will quickly... So two resources that I'm going to talk about, both of them YouTube videos to help you get started on trusses. So there's a guy called HSC Engineering, and in his videos he has one video that explains the method of joints, which I actually like, especially if you have to solve a whole truss, but these days I don't really teach it very much. But because it's in the syllabus, I am required to teach it for a second or two, but then most people and most engineering teachers will then focus on the method of sections. So there's two ways of solving trusses. Most people will focus on that. There's also a lesson on bending, two videos on bending as well. I also have in my collection, I have bending somewhere here, bending there, and a truss question there. So we'll go back, and I will probably add some more as I go on, but for the moment that's what I have right now. Okay, so going back to the book. So calculating the bending stress, and a little bit of a description of when we uniformly distribute loads, shear. So we have talked about shear, but we've never talked about more complicated examples, which, for instance, if we're punching a hole, or if we're dealing with bolts. They're the two main cases that are more complicated that we work about here. Then there's the E equals flea stuff, which you already know. Okay, so moving on, there's testing. Now, I've already talked a lot about testing. I think I have a video, certainly have a pretty comprehensive description on Facebook. Then there's, let's say how many pages on cracks, right? So where does the cracking start? So 1 page, 2 pages, 3 pages, 3.5 pages, right? What's my summary? 3 pages, maybe. My summary: drill a hole at the head of the crack. That is my summary of those 3 pages. Okay, ceramics. So we're talking about glass, right? We talk about bricks. We talk about pre-stressed and post-stressed concrete, which we talked a little bit about already, but not much. Asphalt, which is what we make our roads. Tarmac is for Tar McAdam, because the guy called McAdam was the guy who came up with artificial tar. Tar is a thing that's existed since a long time. Like there's the tar pits in California, but asphalt is asphaltic cement is where we take a man-made product. We take bitumen and we add rock, so aggregates, to get asphaltic cement or asphalt. Okay, laminates, where we talk about different ways that we can make long sections of wood. We're then going to spend a fair bit of time talking about corrosion, and then communication. So here we're really going to focus on threaded sections of bolts. Now, threaded sections are incredibly important. That is something that's almost... Trusses and threaded sections are almost certainly going to be in the exam. And not only do I have examples where I've gone through questions from past papers, but here I have a video that I've recorded where I go into great detail of all the stuff that you need to know about bolts, so that you can go through that. This is another example where I've talked about threaded sections there. Now, I'm not saying like I always say, not everything in my thing is perfect, but it's a starting point. Okay, so in the time I've got left for this video, I'm going to talk about the assignment. So we've talked about the assignment briefly. These are the different outcomes it requires us to do, and we're going to design a truss considering structural and economic factors. We're going to do drawings to AS 1100. We're going to plan our time and manage our time, record our management of our time, and then we're going to analyze our results. Okay, so we've talked about this, but it needs to be uploaded to Moodle. It needs to be all your own work, doctor's certificate. Just know that there are doctors who will come to you, and it's hard to know if you don't have gastro, if you're going to be sick. Design requirements, okay, that might change because we're going to be making our one slightly differently. Report requirements is going to have 3 main sections. It's going to have a design section, a management section, and an analysis section. Design, you're going to come up with 3 different designs, and you're going to pick one of them. Then management, you're going to say what your group did, and you're going to talk about how well they did it, right? So you're going to say what in advance what you're going to do, and then you're going to say what you did do. That's really important in engineering management. Okay, you're going to document your process. You're going to calculate all the forces in your truss. You're going to calculate the critical member, and you're going to write about your load to weight ratio, which is how we're going to assess it. We're going to include your predictions about how it went, whether or not went how you expected, and how it could be improved. I'll quickly show you now a sample of a student's one in 20 seconds. So Here's his report. It's got a title page, got an abstract, table of contents. Could have been a little bit nicer, but here's his suggested solutions. He's got 3 designs and suggestions. Here's his sketches with dimensions. The dimensions are not to Australian standard, and that's really important.